I introduced you today. Who is Batterylog? Batterylog is a spin-off of the University of Applied Science in Bern. That's the academia link. And at the same time, it's a cooperation with the IT company in Bern, 89 Degrees. With this cooperation, we have access to quite a large pool of talented people. And depending on the project that we are running, we build a team with the competence that are needed. So if we do something in the direction of a web application, there we need like front-end, back-end developers and people like this. If it's rather an embedded solution that we are looking for, it's other people that we need. So with this cooperation, we have access to a large pool of people. It's sorry. Okay. We have
just
access.
muted, so.
Okay, thank you, Bruno. To more, you have here 6 people, but we have access to even more people and can do also bigger projects if it's required. With, as I said, always the right people for the right project. The core of our services is a digital twin of a battery. And in our view, this digital twin is something that belongs to the customer. So there's no unique solution. Every solution is different because everyone has a different challenge. What we have is a certain design pattern of elements around this battery twin. For example, if we look at the test automation, most people, when they do batteries, they have something like an end-of-line test where they measure the capacity and impedance and some other metrics. So you can store these values along with a serial number in your twin. And maybe you start with this. Maybe this is your digital twin at the beginning, if you want to start small. And then you might have data from the battery coming in, a stream of real-time data. You connect this also to the twin, you have this linked. Then here we have the battery core. I'll come later to that. That's a service to analyze this data stream that comes in. You might want to have dashboards to display what you have, that the user can go through the data, or you prefer to have APIs to maybe another system at the side. This all depends on you and your setup, what is there. Also, business processes are very important. This can be, for example, if you replace the battery, then it's stored in another vehicle, or it's somewhere in the shelf. You want to model this process and make sure you know where your battery is. So as you see, there are many different sources, and we combine them in a way that this digital twin is really unique for every customer. But with our design pattern, we have a proven design, and we can make sure that we have a quick solution for you. This battery core, I'll come to that later. That's one of the elements that holds the algorithmics. Come later to that. First, let's look at a sample application, what we could do for SPP. So we could monitor these rail vehicles, and here you see our design pattern. So here we have the battery core. This is the generic service, which is the same for all customers. It only holds anonymized data, so there's nothing linked with any customer vehicle or whatever inside. All this stuff we do up there. So here we have a custom-made web application. There we can do everything for the customer. We can do any APIs you desire. We can do any dashboards or any additional things. That's really fully flexible there with this part. And if you look at the data flow now, for this example, data is gathered by the manufacturer of the system, or later the SPB. We hook on this cloud, take this data in. So this is voltages, temperatures, currents over time, more or less. Feed it down to our battery core service. Here we calculate a few KPIs like remaining useful life, put this up here, And with this data, first of all, we can display it. And secondly, we want to put this back to the system of the customer that he can do his maintenance planning with this, because doing the maintenance planning with voltage curves over time is not the easiest thing to do. It's much better to have 4 or 5 key values to make then all these business transitions. So I hope this helps you a bit to see how our setup works. We always do it like this, that we have this generic service and this own web application to have the freedom that we can put for the customer whatever is needed. So let's go to the next stage, overview of different battery models. So the first class I want to show you of battery models are electrical circuit models. They look a bit like this. So you have open circuit voltage, then you have different impedances, that there can be quite many of these elements. And here you have the terminal voltage of the battery. So if you draw a current, so you will have a voltage drop here, and here the voltage is a bit lower because of this voltage drop. These circuit models, they exist quite since a long time, so research is over for them. It's more an engineering topic to do them. They're mainly used for state of charge estimation. Also, the Kalman filter works with these models. Regarding aging, it's not the easiest thing here, because if you measure a battery, it's quite easy to determine all these elements. That's fairly easy. But the problem is, if the battery degrades, then these two elements, they will change, because they reflect the electrochemical behavior of the battery. And then if your model is not correct anymore, then the more complex your calculation is, for example, with the Kalman filter, the more difficult it gets, because these elements might run away. And that's one of the challenges you're facing there. Then we have the class of the physical or chemical models. You see a lot of formulas, and they all depend on a differential equation, many of them. What I said before is also true here. You have a number of parameters that you have to find through experiments, or maybe you know them because you know the cell design, stuff like particle size and things like this that are not obvious to get from a data sheet. If you get this all correct, then these models are incredibly good. You can explore the limits of a battery. Use them, for example, if you want to do the fast charging to find the right or the maximum current before something bad happens inside the battery. You need these physical models. But as I said before, all these parameters are also very delicate in terms of aging. Maybe you determine them for a new battery, but then if you have degradation, it gets complicated. And the more complicated your model is, it might run away. That's one of the challenges. There are regarding research, there's quite some research ongoing in physical chemical models. I feel they will get better year by year, and that's quite a hot topic analyzed right now. Then we have the third class of the battery models. It's data-driven models. It's kind of the opposite of the physical models. Here you want to model exactly what is inside the battery, what's happening, how does these ions transfer and all this. And with the data-driven models, you have more like an outside view. You say, I don't care too much what is inside the battery. I just look what's happening. And like here, you have the mileage of a car, and here you have the remaining range. And that's it, basically. These kind of models are usually used to analyze whole fleets of batteries, and they are often used for aging estimations. Because as I said before, with aging, all the parameters are drifting, and it's getting very complicated to do the aging also with this very precise models. Now we dig deeper into the data-driven models. There are also different classes of this, and we look deeper into statistical models. So statistical analysis is mainly used when you look at a battery fleet, and you're looking for topics like total cost of ownership or warranty questions, things like this, if you look at several batteries. And what is very important in the beginning is that you have to ask yourself, what's your prediction goal? What do I want? If you have this failure, do I want to check this point? This would be like the average aging, or maybe you say, I want a certain failure probability. I don't want that more than, let's say, 2% of all the batteries fail. Then you're at this point. You can do both with the statistical model. You just have to know where you want to go. If you apply then this statistical model on a single battery, or the history of a single battery, then you can get a much narrower prediction of the failure. So you take the same model and you apply it for this battery that has seen quite harsh environments. So you might need to replace it after, let's say, 5 years. And if you take this battery that had the more relaxed conditions, maybe lower temperatures, lower use, this battery you can use for, let's say, 12 years. And that's the main advantage you get. If you use this with real-time data, you get an idea when to replace the battery. Potential use cases are obviously predictive maintenance, but also battery as a service or dynamic usage pricing is also a very interesting one. Now I walk you through the generation of these models in the next slides. It's getting a bit techy. I hope you don't hang up. It's maybe for 5 minutes, then we come back. Huh? So these models, they typically are organized in 2 steps. So there are calendaric losses, which is battery degradation when battery is not in use, just lying around. And then there are cyclic losses. That's when the battery is used, when current is flowing. And both of them are typically organized in a way that you have something like a weighting function with temperature, state of charge, and C rate are the factors that influence this. And then you have a certain scaling by amp hours for the cycling and with time for the calendaric losses. And here with the state of charge dependency, there are things like depth of discharge or SOC range. There are different ways how this is calculated. But in the end, it's always these three elements that are important. So many papers exist on this. It's very easy to find many of these proposed models. But the big question is, how can I tune this to my battery? Because that's a pure engineering question. You have to put this somehow that it works for you. So keep in mind this formula here with the weighting and the scaling. If you set this to 1 for nominal conditions, you get this. You get the cyclic losses equal the scaling. And if you have values, for example, for the data sheet at nominal condition, you can work out your scaling with this. You set this weighting to 1, and then you can set this value. Once you have this, you can attack the weighting functions. The weighting functions typically are semi-empiric approaches. So that means that you assume a certain physical behavior. If you look at this on the right side, this is for calendaric aging. We have the state of charge. There we know we have 2 plateaus. One plateau is 0 to like about 55% SOC, and there's a second one from 60 to 100%. This is true for nearly all carbon anode batteries. It has to do with the phase change that happens here, and you have these two plateaus for NMC or LFP or NCA, more or less. And then regarding temperature, you have exponential increase with the temperature. So it's getting very bad if they're hot. And now, if you have one or two values, you have to tune your expectation of this exponential increase. So maybe you have 2 points, and like this, you can scale your exponential curve with this point. Quite often, you will find positions where you have no literature data, and there you have to go on values from literature, or you have to go for a database with values. We can also help you out with this. We can help you out with the generation of the model and also with the typical values. If you look at values from our database now for the cyclic temperature dependencies are these values. Here you've plotted for different cathode materials, and this is all normalized for 25 degrees. So you see some of the cells, they behave quite heavy if they're warm. Some are even getting better if they're warm. This is quite a big spread between the cells, but in the end, if you look at the dark gray area, you see that here we have 50% of all analyzed cells. So that means all this light gray is just the outliners. And now if you look at the dark gray region, it's not too much. So most cells are in this region. And now you have to ask yourself, where's my application? If you work in a warehouse, let's say your battery is between 15 degrees and 30 degrees. You can say, okay, I don't need to care too much about the temperature drift. I take something from the database, like the median of all these values, and I'm happy with it. If you have an application that really gets hot, like 40, 50 degrees, then I would say you need some testing there because the difference is so high there. And like this, we have values for all the different dimensions, state of charge, C rate, and temperature dependency for calendaric and cyclic aging. Some words on cycle aging, some common pitfalls. You have to normalize this. Normally you have some aging cycles, and you have to normalize this to full equivalent cycles or capacity throughput. Otherwise, you will quickly fail because you cannot compare it. And if you look at the number of full equivalent cycle per cycle for fixed voltage test, that's not constant. If the battery is new, like this, one cycle is one full equivalent cycle because it's discharging the nominal capacity. But as the cell is aging, then the number of full equivalent cycles or the number of amp hours that you get out of your battery is decreasing. And with this example, it's quite an extreme example. It goes down to 0.4 full equivalent cycle, and you have to take this into account when you compare the data. Comparing data is very important because this type of models, they are quite complex. You have many screws to turn, and the combination of calendar and cycle aging makes it quite complex because they add. And what I do normally is I verify the simulation. I simulate the test data I have available, either from measurements on batteries or data sheet values provided by the supplier. So if we take an example here, that's an example of a cyclic test. You see we just have cycle aging in the simulation. The red dots is the values measured in the lab. That's one extreme. Under here we have the other extreme. That's a calendar aging test. So here we have dominated by the blue coming out of the simulation, and we also try to match this measurement. And in the middle, we have a realistic case of a device that has a certain usage, but also has a certain time where it's not in use, where we have the calendar aging. Talking of battery degradation test, their repeatability is really important. And you need to have test equipment with high precision, and there are some things like rest times that are very important to consider. If you don't have a space yet to go, I will go to the BFH Energy Research Center for testing. They have very nice equipment there from Priscilla, who did the introduction. Then what kind of degradation tests you want to run? There, you should make sure that you don't repeat the data sheet. So don't test with the depth of discharge 100% because no application runs a battery with this. Or at least I don't know any application that really drives down the battery down to zero, and then if you have a vehicle, it's dead. Everyone uses something like DOD 60, 70, 80% maybe maximum. So make sure you test at the typical operation point. And also ask yourself if this type of fixed voltage threshold tests is really the right thing for you, or if it's maybe better to go for a fixed discharge profile. So a fixed discharge profile is something like, if you imagine you have a truck and this has a certain route, has to deliver some goods, and this needs a certain amount of energy, and this energy this is your discharge profile, and you run this profile out of your battery while it's degrading for the test. So from my perspective, this gives you a way better idea how long your battery will last compared to fixed voltage tests. With the setup we have here, we can simulate any kind of these tests for doing the model. For low budgets, I would recommend you to do one cyclic and one calendar test point at the most common points of use. And if you do this and you don't need temperature extremes, then I would skip all these exploratory tests. And still, if you do this, it gives you quite a good feeling where you are compared with the datasheet. Because again, datasheet is typically with DOD 100%, and this is not what you typically have. Getting back to Batterylog and the battery core features, the features that are available today, we have developed a matrix-based state of health engine, which means that the battery models, they are organized as a matrix, as a lookup table in different dimensions that we store in a database. So we can run this state of health engine on real world data and provide you individual state of health estimations. For every single battery, if you hook on 100 battery, you get out 100 different values depending on the usage of your battery. We also have a simulation mode for analytical use cases. If you want to simulate certain cases, that's also possible. And we can provide you with default parameters for a quick start. You can anytime change these parameters. For example, if you're growing and you have more data yourself, maybe you have done a battery test, maybe the battery supplier gives you more value, or you have some learnings from the field, we can tune your model anytime. The way this is organized is that we just change this matrix and then it's all good. We also have a backend for graph data such as histograms. Specifically temperature histograms, are very common used to look at the battery data. If you look back for a battery usage for 10 years, it does not help you to plot this over time. You need another form. And if you have data looking back for 10 years and you want to do histograms, yeah, it's also quite a calculation that you have to do. And what we have is like a standard for typical graph data, that the data is prepared and available in a quick way. So if you build a dashboard, we deliver you the data very quickly for all these default graphs. And we have APIs for data exchange. We can exchange the data with this custom dashboard, or we can exchange it also with your own. Maybe you have a customer relation tool or whatever where you want to have this data, and you can get all this there as well. So that's what is available right now, but we also have a full development pipeline. The first thing we will realize is a impedance calculation should come by end of this year. Give you a quick preview later. Then an online state of health estimation. This is independent of the statistical model. So when I speak of online, I mean that it runs on the data that you record. So you drive a vehicle and you have any arbitrary drive profile. You upload this data, and at the same moment you have this data analyzed. For the statistical model, you need the data from point zero that it works well. For this online state of health, it should be possible to just get a few cycles and get an estimation on this. It's yet experimental status, and yeah, should be coming next year. And then we want to do battery fleet summary analytics. That's also on the to-do list. And we want to apply the battery core functionality for single maintenance tests. So for all these people who don't have their data on a regular basis uploaded, but maybe just test the battery once per year, we want to make sure they can also use all the intelligence we provide here. And last but not least, we have also a to-do list with artificial intelligence for automated model tuning and to improve the forecast. But that's then, yeah, something for later. But as you can see, we really we are on the topic, and we improve this course step by step. The way we improve is basically that we do this customer centric. So whenever a customer asks us to make a battery fleet summary, this will come earlier for sure, because we prioritize this depending on our customer. So looking at this impedance estimated that should come by end of the year, this is intermediate result data. It's captured from a vehicle that is running on the road, doing the cycles just as it does, so no specific steps or anything. And as you can see, we have here plotted the temperature, and we can even see that the impedance is higher at a lower temperature, and the impedance drops slightly if you look at it by the eye. What is also obvious that there's quite some outliers. So how to filter is absolutely key for this type of algorithmics, and that's also the main challenge to get the right filter and the right method to get rid of the outliers. But as you can see, we're on the topic, and we're doing progress. So coming to the use cases, one of the obvious one is predictive maintenance. So instead of replacing all the batteries, for example, after 5 years, you replace it depending on usage. And this leads you to a longer use of the battery. So you improve the total cost of ownership and also your environmental footprint, because you keep the batteries longer in service. We also work on an early detection of bad batteries. For example, with this impedance estimation that I showed you before, or the online state of health, this should trigger you an alarm if one of the battery is aging faster than the the statistical model would assume it to age. Data-driven analytics is getting more and more important. So you can use the real-world data to analyze your product. For example, you can see how your customers use the battery. Do they, how much they discharge? So whenever you rework your product, you might work on the size of the battery or do things in a different way. And you can also develop your own data-driven metrics for a business process. So one potential business process is if you have a truck and you have like a long run, you have a long delivery line and you have a short one. Then the new battery for the new truck, first you do the long run, and after a certain time you put it on the short track. And this kind of things you can do data driven with data from us. No vendor lock-in. The question is, do you really rely on your battery manufacturer data? Some of them are logging values, but if you have a warranty case, I'm not sure if they really blame themselves that they have to pay the warranty. And also many people don't trust them in the end. So I think it's better to get your own data. And regarding consulting, we can also make sure we don't do any money with selling batteries. So we are completely independent. If you ask us for an opinion, we will give you this opinion without any stakes somewhere. Another use case is new business models, very interesting. Second life is the obvious one, but also battery leasing or dynamic usage pricing is very interesting, where you provide the battery and you charge them depending on the usage of their battery. So the people who treat the battery bad, they have to pay more. I'm sure there are additional business models. Maybe you find new ones. But it's interesting what you can do with these data-driven approaches. Warranty, I already spoke a bit on warranty. Usually you have warranty conditions like temperature windows, and you have to guarantee that you did not exceed these conditions. And this is also something you can do with log data. If you give yourself warranty to someone else, you can use the data to quantify the risk of things like warranty extensions or service contracts. And finally, the traceability is also getting more and more important. Carbon footprint is a big topic there. There's also a digital battery passport coming, pushed by the European Union. That's definitely also one of the topics that is quite hot with us, and we plan to provide this passport as soon as it's available. Again, to our design pattern, we provide a flexible integration dev. So if you look at the green blocks, it's the blocks we do. Maybe you look first just at the right half here. Here we provide everything. Customer just has his application. We can provide you IoT systems, cloud services for IoT, getting the data into customized applications with dashboards and whatever you like, and hooking on our battery core to calculate the KPIs. Or we can do the opposite, where almost everything is in the hand of the customer or is already in an existing proprietary application, and we just provide you one part of the puzzle. We're really flexible. We do everything in between there. Just ask us what you need, and we will find a solution. Why Batterylog? We have proven design patterns around battery applications, so that's mainly what we do, software for battery systems. We develop individual solutions. We're not just a platform. We really want to develop this together with the customer and build solutions that make the customer happy. We also used for agile implementation, which means it's not just a word. It means that at every end of a work, you have a running implementation. and you decide yourself when it's the next time to upgrade this application. That's also quite a nice way for a customer to control the features he wants to have, and also to keep control of the costs. As mentioned before, we have a full range of specialists available. We develop a team depending on the project. We have from IoT to embedded software, from web applications, front-end, back-end, up to hosting and maintaining IT services. We have everything needed, plus, of course, the battery systems. And now, if you're not a customer, but someone looking for a job, we don't have any positions open right now, but this might change in the coming year. So if you have experience with a Django, data science, or physical battery models, or if you're a full stack developer, give us a call, and yeah, let's see the office in the center of Bern. We have quite a nice office and very good conditions also for part-time workers. That's would be nice if we get some feedback there. So I'm close to the end. Just to show you the companies where we are working with. We have quite some big names already, and there are a few ones that we hope to join us soon. So I'm at the end and open for questions. Thank you.
So thank you, Stefan, for the presentation. We have, yeah, okay. I wanted just to say that you can raise your hand or maybe just write the question in the chat, but we can start with Frieder Herb, please.
Yes, hello. Thank you for the nice presentation about really this tough topic, battery aging, what I know since many years. But it was very interesting for me to see that you point out this calendar aging and the cycle aging. Still, my feeling is, and I want to know from your side, that we have also this combination, especially when we look at fast charging. So that when we charge, that we have also a high part of calendar aging during charging. You agree also on that?
Yes, if it goes too fast charging, then presumably it's also at the limit of these data-driven models. Then presumably you have to dig into the physical models. That's my feeling. But I agree with you that if you work with very high currents or also with low currents for a long time, you see that the calendar aging it's not the same as if there is no current. So it's an aging. I also heard the term exposure time, the time it is exposed to a certain condition. Our state of health engine could even model this exposure time because it's like something that goes. Maybe I can jump back to the slide if I find it. So we are here, and if we look at the calendar losses, normally this C rate is 0. The current is 0, so you just have a temperature and state of charge dependency and the scaling with time. Yes. And if you have exposure time, then it means that you have at the same time you have here a current flowing. And it's possible with our approach that you can put some weight to model this this exposure time there.
Mm. I think you will always considering with the cycling, right, Stefan? Because anyway, the cycling is taking a certain time.
Yes, for sure, yeah. So the normal models, I use the same weight if the C rate is 0 or if there is any value here. So if you have, for example, you discharge with 1C, you have 1 hour here, and it does not matter for most common models if this hour is now with current or without. But it would be possible in the table that we make a dependency here on the current, and we can also change it by the C rate or change it by charge or discharge to really simulate exposure time. but I have to say it's rather complex. You need data to match it to develop these models, but it would be possible.
Yeah, because I see also always in reality there is no difference between cycle aging or cycle losses or calendar losses. So they're always combined, and then that makes a problem.
Yeah, in the reality they are combined because you just have a certain aging process. But if you have your simulation, you have to cover a set of conditions. Then you end up in a simulation something like this, that you see that there's some part is calendar and some part is cyclic. So if you do simulations, then you should be able to simulate a certain extent. And here, if you look at this, you see that this small cyclic part, that's just the diagnostic tests. So in this, for this example here, cells were held at a constant condition for like 6 weeks, I guess, and then we had this diagnostic test. So you see that diagnostic test is also aging the battery a bit. And if this is only a tiny bit compared with this, then the test setup was good. And but still it is combined. It's always, you have both of it.
So, but you consider in this case, if you have zero current, then it's calendar aging, and if you have a current, then it's cycling aging, I guess.
No.
In this graph, I will say.
In this graph, there, yes. In this graph, no. Here I have the exposure. The exposure would be the time aging when current is non-zero. But this is nearly not existing, because in these setups it was not. So there's a very thin line in the middle here that is not visible.
Okay.
But it really depends on your battery, and you might do the model in a way that this exposure time is really something that is important. If you have a condition where this gets very important.
Okay, thanks a lot.
Welcome.
Other question? I have one.
Okay.
For the impedance, the estimation of the impedance, I don't know how much you can disclose, but are you sure that in what you do, you always are at the same SOC? Because we know that the impedance is changing by varying the SOC of the cell. So how can you be sure about the SOC at which you are and at which you are computing these estimated impedance?
I know at which SOC I am, also at which temperature. I could do you a plot like this when we have this axis here with the state of charge. The problem is that this is always multi-dimensional. You have these points, and every of this point has a certain temperature, it has a certain state of charge, and it also has some certain other conditions that make this point maybe valuable or not. And
this is what, when I saw
challenge.
the plot, this was my main concern, right? That maybe you are comparing their different SOC, but of course, I know that you know which are, but after what,
so for sure, one part here is also the state of charge distribution, presumably. If you look at a certain temperature, all at the same temperature, you might have a certain range that is state of charge distribution. But also I have to say, for my what I've seen so far, at least with these batteries here, is that it does not change too much in the range of 20% to 90%.
80, yeah,
or 80,
yeah, especially low SOC, it's tricky. Yeah. Other question?
Hello.
Hello.
Okay. Sorry. I have a quick question. You mentioned it just as a side note for the business models, the second life applications. Do you have someone already building a business based on that because my question is, would it be reliable enough to predict I can sell? Let's say I have a company that produces battery packs. I have all the data, and after their primary use, I want to resell them at a reduced price, of course, but still at, well, let's say their value. And of course, I have to give a guarantee. And if my prediction fails, then I make a loss.
Yes, so at least you're much better with such a setup compared to just guessing. So at least you know what your battery has seen, and predicting the future is always it's always tricky. By the way, this battery passport, this digital passport by European Union goes exactly in this direction. So there will be some standards defining how the battery is used. So you have something like a standardized paper that goes along with your battery that you can say what is the status, and this should also help to give a value to the second life product. And maybe to the first questions, one of our customer is doing business with second life batteries, Libation, and it works quite well for them, I guess.
Okay.
But they are quite new batteries, right, Stefan? So what it is the
Yes,
average
so,
age of?
Yes, but if people throw away quite new batteries and they select the batteries, and
I thought that Markus was mainly referring to the fact of having a reliable estimation at SOH that is lower than 80%, something like that.
Yeah,
so when you are close to the knee point of the battery decay. But
it really depends on cells might be so different. If you look at this, this is a discharge to 40% state of health. And if you have something like this and your battery is used in the first life until 70%, about here, I would be absolutely confident to use it down to 50 or even 40. But there are other batteries that don't behave so nice.
We agree.
I also have a question, Andreas Fuchs, Swiss Federal Railways, regarding predictive maintenance. Were you saying that you look at the lumped parameter like impedance of the whole battery, and once you see a change, you dig deeper and check on the cell level if cells or maybe a module has to be exchanged, or what? Or do you have to anyway look deep down into the battery, look at every cell or every module?
The predictive maintenance is something we do really customer centric. I think there's no general way to do it. It also depends what is the unit you can replace and what's the time you can replace. I know for the rail sectors, you sometimes have your maintenance interval that you have maybe every 4 years. You have the chance to replace the battery with a bigger maintenance interval. Then the main question is, how confident am I that this battery can last another 4 years? And maybe for another application, this is not the question. It's maybe a different one.
Okay. Thank you.
Welcome.
So, if we don't have any other question, I think I will thank you, Stefan, for the very nice, interesting presentation. And yes, really looking forward for the next development that you will have in the next month and year. And I thank you, everybody, for the attendance. And we will see next month with Battery Europe, the 4th of October. And yes, so thank you, everybody. And don't forget the battery iBAT workshop, the 28th of September. So thank you, everybody. Have a good afternoon and see you soon. Ciao.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.